Thank you very much. What an awesome introduction. So let's get started. Like I said, I'm going to talk about resilience engineering in a microservice landscape. That's what we do at bol.com. But first, let me introduce myself. My name is Maurice Zeijen. I've been a Java developer for over 10 years, and currently I'm a hands-on lead architect at bol.com. So for those who are not familiar with bol.com, very quickly, bol.com is one of the most popular web shops in the Netherlands and in Belgium. And we have about 28 million visits per month, sell about 14 million products to about 7 million active customers. And I have about 1,200 colleagues, and as 350 in the IT department. So, what am I going to talk about? First, what is resilience, and why do we need that? Why do we care? Then we're going to see how Hystrix is going to help us in that area and implement it all for us. And then we're going to take a look at some resilience techniques via an interactive demo, and going to see what happens if you don't apply those resilience techniques and the difference when you do. Finally, I'll get some tips and tricks that we learned at bol.com, and we'll look at some operational stuff and some general experiences to end with a wrap-up. So what is resilience? So it's the ability of a substance or an object to spring back into shape, or the capacity to recover quickly from difficulties. Well, that's the real world. Like, for instance, a bungee cord. Like, if you're jumping and the cord stretches, then that cord is really resilient against those tensile strengths. But when it returns back to shape, well, it's really resilient against that. So that's cool. Or, like, you and your colleague are sick. You take only 2 or 3 days to recover, and he takes about a week. Then you could say that you're more resilient against the flu, for instance, than he is. But we're in an IT system, so what does it mean for IT? Well, it's the ability of a system to handle unexpected situations without the user noticing, preferably, or at least with a graceful degradation of service. And really important, it needs to be able to automatically recover as if it never happened. You don't want to restart your application just because some error occurred. So that can be a really broad definition. So what I'm now going to talk about is this situation where you have an application like the bol.com web shop, which is still a monolithic thing, and it talks to about 40 backend services. And it does that via REST, direct calls. And it's mostly still a bit of a blocking architecture. And in those cases, you need certain resilience techniques. So if you're in an event bus situation or a messaging system, then you probably need something else, or you need less of these techniques. So why do we need it? So failures in today's systems, certainly with a lot of microservices, interesting. It's not the exception, it's normal. It happens a lot. Certainly if you have a lot of systems, a lot of things can happen. Let's see, this helps a bit. OK. So for instance, what does complexity mean at bol.com? Well, we have more than 50 user-facing applications, which are talking to about 120 backend services, and about 60 IT teams that are messing with that. So you can already expect a lot of problems occurring there, and we need to be resilient against that. So what can happen? Well, one of those backend services would simply fail and go down. Or maybe that team implemented a new version, and that new version has certain bugs, or if it's even not backwards compatible. But it can also be the network that can degrade or fail. But it can also be your own application having issues with that new client library that you're using to connect to that backend service. And the most worst thing that can happen is that a backend service becomes slow. And the reason is that latency, it's infectious. It can spread through your whole microservice landscape, even to parts that don't really have anything directly to do with the system that is actually slow. And I will demonstrate that later on in the demo. So we need to be resilient. And this is an example of Texas in 2008, where a hurricane came by, Hurricane Ike. And this was a nice neighborhood on the coast. And only one house was really built to withstand those hurricane conditions. And well, the rest is the result you see here. So Like I said, I have a demo running. It's actually running on my machine now. And it's a mini service landscape. So we have this fake web shop, and it has a product list page. And that product list page, well, it shows products, and it talks to a product service to get those products. And if you click on a product, you get to the product detail page, and it talks to the product service to get its product details, but also to the review service to get a number of reviews. This is the example shop, so it's really nice. Proud of it. And like we see, we can click on it, and we see it has a couple of reviews. Well, nice. And in my demo, I can start messing with the review service. So I can make it slow, I can make it fail, I can turn it off. And we're going to see what happens to the rest of the web shop when I do that. But first, I'm going to talk about how I'm also going to protect it. And like I said, we're going to use Hystrix for that. And Hystrix is a library built by Netflix, and it is there to protect you against latency and fault tolerance, faults. And it provides a means to be graceful in your failures. And it measures about everything it does, which gives you a great insight. And we'll see that later as well. And it's fairly easy to use. And there are similar libraries on different languages, or even different versions on the JVM. You should check them out. But this is all based on Hystrix. So in Hystrix, where do you put in Hystrix? Well, you put it in the application that you're trying to protect. So here we're going to try to protect the web shop, and we're going to put it in front of the client library. So the client library, it's mostly an HTTP client, and every call to the HTTP client is going to go through Hystrix first. And Hystrix has this flow of doing things to give that protection. And you don't need to remember this flow now. We'll walk through it during the presentation. So let's start with the most basic stuff, and this is the Hystrix command. The Hystrix command is what it is encapsulating your call to the resource. And if everything is fine, it will return the result to your application. And if we look at the most basic way how you implement that, and there are less bloated ways to do that, but we're not going to look at that now. But this is the most basic way to do it, is that you create a class which extends a Hystrix command, in this case returns a list of reviews. You give it fields for everything it needs to do the call, and then you create a constructor to get all those fields into it. And then you implement one method called run, and in that run you simply do the call to the client. So here we have a review client, says get reviews, and you provide it with the product ID, and it returns you a list. So you do this for every endpoint, not one command for a whole service, no, for every endpoint. And if you want to do this in a non-blocking style, because this is blocking, then you can implement the Hystrix observable command, but I'm not going to look at that as well. There's a lot of good documentation on there, so you can take a look at yourself. But first, how do you execute this? So you create a new command, provide it with everything it needs, and you say execute. And this is the synchronous and blocking manner, and you do this every time you want to do a call. You're not going to reuse this command. It's a bit weird, but it's just how Hystrix works. If you want to do it in an asynchronous blocking manner with a future, then you can do that. You create the command, say .q, and then you get a future and you do your thing with it. It's rather a normal future. It's not a completable future, so you can probably forget about it. We also have the asynchronous manner using RxJava, and then in that case you say .observe, you get an observable of the list of reviews, and you do your thing with the observable. And this is RxJava 1. There is no support yet for RxJava 2 or for Reactor. If you're interested, hopefully at some point it will start with Hystrix 2 and it will have that support. You can also do streaming, where it's similar, but then you implement that Hystrix observable command. And here you see again .observe, but now you get a callback for every review that comes over. You don't have that list anymore. Again here, back pressure is not supported, too bad. But to be honest, often you don't need that if you're in this style of application, so don't worry. So let's look at these resilience techniques that Hystrix gives us. First, the fallback. So the fallback is the way to gracefully fail, and Windows in the past wasn't that graceful. We all know this scream, right? So the goal of the fallback is to try to give the user which can also be a different system, to give the best possible experience when your system is having issues. And you can do that in several ways, and a couple of examples are you hide the feature, it's very simple. You use a default, which is called a static fallback, or you try to get an alternative, which is called a stopped fallback, or a fallback via network. And not always a fallback makes sense, and we'll look at that in a couple of slides. So, where does it happen in this scheme? So we have this call to the resource, and when it fails, which can be an exception, or, then we go to the fallback. So the fallback, if it's implemented, and it doesn't fail itself, then we return the fallback, very simple. If the fallback itself throws an exception, or you don't have a fallback, then we will return the exception as normal. So now let's look at the demo shop again. So we're going to look at a lot of these graphs to see what is happening within the web shop. So here we have the product detail page and the number of requests it's getting, and the same thing for the list page. And below we have the distribution of reviews over all the detail pages. So we see that most of them have about 3 reviews. And if I go to the shop again, then we can see if I go to the first product, that it has 3 reviews. Oh, nice. So now let's see what happens if I turn off the web shop. And to prove that it's actually something that's running on my machine, I have the Spring Boot application that I'm simply going to kill. And now we see, oh, errors are happening. It's not that nice. So if we go to the web shop again, and I click on the first product, then, this is not what we want, right? We don't want to give the user this experience. This is not really nice. Too bad. So in my demo setup, like I said, I can enable and disable certain Hystrix features. So let's enable the fallback in this case. Now we see, oh, all the calls are successful again. Oh, nice. But the review distribution is 0. We have no reviews nowhere. So if you go back to the demo shop, go to the first product, and indeed, it works again, but we don't have any reviews. Well, so this is a really basic example of a fallback. Another example that we also apply at Bullet.com, we have a lot of them now, but this is an example that's called a stopped fallback, and it's about this title page on a product list page that we have. This title actually comes from a service, and this service uses the category that you're on and the filters that you have applied within your search to determine which title and which text it wants to display. So what happens when that service simply is down or slow or whatever? We simply fall back to something that we gave the command, which was that category, and we simply show the category title. Well, it's really easy, but the customer probably won't notice. So, like I said, not always a fallback makes sense. And a couple of situations where you don't want a fallback is, for instance, for a write operation. It would be really awkward if you would say to a user that you accepted his order when you actually didn't, because there was a failure. So you would simply want to inform your customer that it failed. You don't want to lie in that case. But it can also be if you're starting some batch job or something else in the background, you want to inform that didn't work. And we've also noticed that within a backend service, so certainly more the core services, it's really hard to define a decent fallback. So often what we do in a backend service is we don't have a fallback, we simply still throw an error, or we give the fallback or a partial result of the data and give some metadata back that informs about, okay, here is some data, but it's not 100% correct. Maybe you want to do something with that. At least you fail fast. That's really important. You're not going to wait for late timeouts and other things. So where do you implement this fallback? Again, we have this get reviews command and a Hystrix command that extends the Hystrix command, and you add this get fallback method. That's it. And in this case, we're returning an empty list. It's really simple. What if you don't have a fallback? Well, in that case, Hystrix will throw a Hystrix runtime exception. So you want to catch that somewhere, and to get the actual exception, you say exception get cause. So, next thing, latency. So every call to the resource is being monitored on how long it's running. So, and when it's running too long, you will get a timeout. And if the timeout happens, then it will try to do the fallback, and well, the rest you know. So again, back to our demo. In this case, I won't do any fallbacks, I won't do any timeouts. Let's see what happens when we do that. So let me increase the latency to 1.5 to 2 seconds. So we see a couple of things. For one, we're not handling so many requests anymore. Everything is becoming slow, because this is the client latency you see here. So we get a latency of more than 7 seconds for the client. And here below, we see the thread usage, and we see that the product details page is now using more than, well, 49, 47 threads. It's not that good. To be honest, I intentionally limited my system that it's not using so many threads that a normal system would do, because I don't want that thing to catch fire. So it has a limit of 50 threads. So this isn't really good, right? So let me first make it recover. Okay. Now simply set a timeout for 1 second and enable it again. Oh, now we see errors happening because, well, after a second we get an error and I don't have the fallback enabled. But we see that the time that your customer is now waiting is a lot less. It's still a big amount, it's 2 seconds, but that's because we're still having a lot of thread usage. And that's what I'm going to talk about next, and that is we want to prevent that. And to prevent that, we're going to use bulkheading and load shedding. So here we have a ship, and it has bulkheads. So the Titanic was one of the first, but they didn't really implement that correctly. Later ships, it was more successful. But the bulkheads are these bulkheads in the ship that prevent it from sinking when you have a hole, because the water can't flow throughout the whole ship. Where do we have this bulkhead in the schedule? Well, if you're executing the history command, before that we go to the resource call, we have a semaphore or a thread pool, and that's going to limit the number of concurrent calls you have to the resource. So let's say we set it to 10. That means that if 10 calls are in this area here with the call resource, then the 11th comes in, and we're going to reject it. And when we reject it, we're again going to go to the fallback. So again, a lot of graphs. So product detail requests, the latency of the product detail page, the distribution, now also the list page, and the list page latency, and the thread usage. So now, if I increase the latency, and I'm going to increase it really, really high, to 5 seconds, we see something interesting happening. So, okay, that the product detail page will become slow, we know. But we also see that the product list page is becoming slow. Really slow, actually. That's weird, because the product list page is not doing anything with the review service. But all the threads are being used by the product detail page. So yeah, this is bad. And this is where the whole cascading effect comes in. And even if I set it to 1 second, so let me recover it quickly, set it to 1 second, try it again. Even now, give it a bit, but even now we see that the product list page is becoming slow. We're using not as much threads anymore, but still, it's affecting the rest of the system. So this is where this cascading effect comes in. So let's say we have this landscape with a couple of services, and the root service becomes slow. It has a lot of latency. Then, of course, you can expect a direct effect on all the services that are calling it directly. But because all those connection pools are filling up in those other services if they don't apply any resiliency, you will see that all the other endpoints also become slow. Well, and then it explodes. So you have a big problem. Of course, this is only when you have a really high load on your system and you don't have any things like caching or other mitigating parts in there which make it less worse. But this is not like the perfect storm. So we can protect against it using bulkheading. So let's enable bulkheading. Say 10 threads, timeout, 1 second again, it's fine. Give it a huge amount of latency and enable that. So now we see a huge difference. Yeah, okay, the product detail page, we still have those errors, and I can fix it with the fallback. But it's not slower than 1 second. But the list page is not affected, doesn't care. there are still enough threads left in the system to handle those requests. So this is huge. This is important. So I talked about that you have semaphores or thread pools. So with thread pools, I want to talk about the difference. And you can have both with Hystrix, and per command you can choose. So if you're going to choose for threads, it has a couple of advantages versus semaphores. So when you use threads, the calling thread can always walk away. If the timeout happens, it can simply continue with its other work and no problem. And Hystrix can also try to interrupt its own thread that is just doing the call to that client, in the hope that the client will quit doing its thing. The disadvantage, however, is that every thread adds a little bit of computational overhead and memory usage. But to be honest, we do this a lot within our web shop. We have more than 40 thread pools, and we notice nothing. We have no problems with this. It's just fine. A more bigger disadvantage is that a thread pool is harder to tune because a thread pool can be shared by multiple commands. So semaphores, they are awesome because they have a very low overhead. And they're also easier to tune because every command has its own semaphore, always. However, it of course has a number of disadvantages. It only limits the concurrent calls, but it doesn't fully isolate, so the calling thread, it can't walk away because it's the same thread. It needs to wait until the client is finished. And interrupting is also no possibility in that case. So that's why when you want a recommendation, then I would recommend starting with thread isolation, except when the thread usage is really, the overhead is really too high, or you're using a client where you are, a client that you trust, and that you can do client of a request-based timeouts on. And if you're in a more asynchronous, non-blocking environment and using the Hystrix observable command, then you're using the semaphore by default, because then mostly the client is doing the thread handling. That's fine. So before we go into the last resilience technique called circuit breakers, I wanted to look at metrics that Hystrix is exposing. So this is an example of one command from the Hystrix dashboard, and it gives you a lot of information, like latency information for that command, the number of calls that were successful or failures, and also a cluster view. So what does that mean within our overview? So all these different parts of Hystrix are generating these metrics, and they are simply reported to the outside world. You can use that. And I want to give you an example of the actual bol.com web shop at this moment. So this is what is actually happening on our shop. This is this overview of all the commands, and I can scroll through it, and you see we have a humongous amount of them. And this is a live view, and mainly just used to give a feeling of what is happening with your system. If you want to do more analysis, you can go to a more historic overview. We use Grafana for that. And hopefully it loads. Yeah. So here we see an overview of what is happening with this command this day, today. So we have a number of executions. We see some failures coming by, timeouts, and we see the latencies coming by. Well, this is really useful because you get a completely new overview of what your system is seeing versus its backend services. So now I need to, yeah, okay. So these metrics are really useful, and you can use them for monitoring and alerting. But they're also used for the circuit breaker. And the circuit breaker is like a fuse in a fuse box. If it's closed, it will let current through, but if it opens, then it won't let anything through, and you don't have power. And where does this thing fit in? So you execute the command, and then the first thing it's going to look is at the circuit breaker. And the circuit breaker determines, by looking at the health of the resource, if it is open or not. And if it's unhealthy, then it will open, and everything will short circuit to the fallback. So how does this look? How does this work? So we have three states: closed, open, and half open. When it's closed, everything is fine, but when we see too many failures, which by default is 50% of all the calls, if they're a failure, then it will open. And everything will really fail fast, because everything will go to the fallback immediately. But we need to automatically recover, so sometimes it will try one request, I think every couple of seconds. And then it comes into the half-open state, and when that one request fails, we'll go back to open. But when it succeeds, we'll close the circuit breaker immediately. So last demo. Again, all the graphs, so page requests, product detail, latency, distribution, request for list page, but now we also have a circuit breaker overview, and again, the thread usage. So now let's immediately enable certain resiliency things, but not the circuit breaker yet. Oh, not this one. And let's make it a little bit slow. So we see now that the error percentage of the circuit, of the command, is going up and up and up. But because I haven't enabled the circuit breaker yet, it's still close, you know? And we still see this thread usage of 10 threads. Yeah. So what happens when we now enable the circuit breaker? Well, it will immediately open. But the big difference here is in the thread usage. All the threads, you know, they're gone and not being used. Because the Historic circuit breaker says, well, this thing is not healthy, and not even going to try to call it. And because it's not even going to try to call it, the backend service actually has a breathing room to recover. That's a nice side effect. But also, every customer hitting this command, you know, they will get awesome performance. It's perfect. So when we reduce the latency again, let's say to 20%, then this should start recovering in a second. Yeah. So we see, oh, the circuit breaker closed again, but we still have a little error percentage left. Okay. So these are all the things that Historic is doing for us. Now let's get into some tips and tricks that we encountered while building this into our systems. So first, make sure when you start with this from the beginning that you set up monitoring and alerting. Because if those circuit breakers are open, then the only way to know that is because customers start complaining that certain features simply are not working or always empty or whatever, you know, if you have a fallback. So you need that monitoring to discover what is going on in your system. And we actually split it up in two certain types of monitoring. We have critical and non-critical commands. Because certain commands, like for us, searching in our web shop, if you don't have that, then our web shop doesn't really do a lot. We make them critical, which means if those circuit breakers open or the failure rate is too high, then our ops guys and the team responsible will immediately getting messages, hey guys, you need to do something. But certain things, like reviews, they're not critical enough that we want to wake up somebody in the middle of the night. So in that case, it's just a non-critical service, and we get a warning screen somewhere on a monitoring screen or whatever. So another thing is, don't forget to configure those clients, those HTTP clients, because they have also timeout settings, and you still need to set them correctly. And also the connection pools need to be big enough to be able to handle all the requests. This is something that is often forgotten at our company. So why is that important? So here you have a normal execution where you have an application thread calling the Hystrix command on that same thread, and it's going to start this Hystrix thread and do the actual call to the resource. If that resource is slow and it's timing out on the Hystrix level, but the timeout has not decently been set on the client, then that Hystrix thread is still being used. It can't be released until the client simply, well, it is done. So this will cause unnecessary load shedding if you don't configure this correctly. And with semaphores, it's even worse, because with semaphores, the calling thread can't walk away. So you will still have this whole latency problem, well, less because you're limiting via the bulkheading. Yeah, but it's not good. So two things you can do. You can make Hystrix timeout of the client timeout before Hystrix does. That's fine. The only thing is Hystrix won't know that it is a timeout causing this, so it will simply return an exception, and the metrics you also see it just as a normal failure. If you make the client the timeout just after Hystrix, then Hystrix will understand, hey, this was a timeout, how nice, and it will also register that as a timeout. But you can also do a different thing, and it is implement a hook, because Hystrix is really pluggable. What we do is we have this map. This mapping function is timeout exception, and it knows all these common Java timeout exceptions, and it will map it to a Hystrix timeout exception, and that way Hystrix also knows, oh, this was a timeout. And this makes it a lot easier. It doesn't really matter anymore who times out first. It's always registered as a timeout. And another trick is what you can do is make the client timeout always have the same timeout as the command, because then you need to configure one timeout less. So what you can do in your history command is get the properties of that command. You can get the execution timeout in milliseconds. They really love their long method names. You get the value of that, and you simply pass it along to your client. Your client must be able to deal with request-based timeout settings, though, and not all do. The same thing is with retries. Some clients tend to do retries automatically. You need to be careful with that. You don't want to have too many, because then you have the same effect as having a really long timeout setting for your client. So if you really want to have retries, do at most one. If the second one fails, then something is probably really wrong with your system, and, well, let it fail. Next thing. Commands, groups, and thread pools have names, and those names are really important. You need them for configuring your commands, so they need to be unique. But also, you see them everywhere in your monitoring systems and your alerting systems. So they need to be really descriptive and tell what that command is doing. So what we do is we incorporate the service ID, so the short name of a service, what we're calling, and the command name. And the command name should always say what a command is doing. So for instance, we have this PCS service, product content service, which gives product information. We have this method get product by ID. If you see that in a monitoring system, then you immediately know what is going on. Tuning, really quickly. When you're tuning is really important for Hystrix, you need to do that, you can't ignore it, and certainly if you have high loads or long latencies. And you should be tuning based on production information. And you need to tune it on the behavior of the resource and not on what you would like the timeout to be. So if you have a resource that you're calling, and its normal behavior is to have a timeout of 1 second, then that needs to be the timeout for your command. But if you don't want to wait a second, but maybe only half a second, then you need to add an extra layer of timeouts around that and say, oh, I only want to wait half a second. Else the timeout will always give errors because it thinks that the resource is unhealthy. And again, don't forget the timeouts of the client. So I have this overview of different formulas for these timeout settings and concurrency settings. I'm not going to go through them now. If you download the slides, you can take a look at them. And similar ones are also on the Hystrix wiki, so you can take a look at there as well. And for the client timeout, something I noticed is the connect timeout. People tend to set that to seconds. A connect timeout is when the timeout that you need, of the time a service needs to connect from one service to another service, but not to deal with the actual call. Often within our network, 100 milliseconds is already a very long time, so you can use that or even lower. If you're going to another network, it can be a different thing. In that case, measure these settings before you're setting it to seconds. And for the read timeout, we've already seen it. When you're not using retries, you can set it to the command timeout. And if you're using retries, one retry, you can say, OK, take the 99.5 percentile resource latency. It should be the plus the median resource latency, because you expect the second call to succeed. So, small things about operations when you're running this on production. You will see jitter and failure. You already saw that in an example from the Bullet.com web shop. There will always be some timeouts. And that can be because of garbage collection, or maybe a new machine is starting up and it's warming up. Or you can have different payload sizes, where sometimes the payload size is simply too big and it takes too long to handle. And many other reasons. So for example, this is the PCS service again. And it handles about 200,000 requests in 30 seconds. But you see that it also has about 250 timeouts in that case. And when Hystrix is starting to report failure, a circuit breaker is, for instance, open, then don't overreact by trying to retune that circuit breaker immediately. First, see what is going on, and determine if it's not really a problem in the backend service. And if you determine that everything is fine with the backend system, yeah, then maybe you want to do a retune session. So, some global experiences at Bullet.com. It already prevented a lot of small outages and a couple of big ones. And because of that, we sleep a lot better now. So it really helps. Our operations guys are really happy with this. And Hystrix in itself is a great library, although it's starting to get a little bit outdated. But in general, it does its job well. It integrates really well with our tools because it's pluggable, and it's easy to learn and implement. However, tuning is often overlooked by our teams, and it's not trivial if you're going to do that. So we often see incorrect timeout settings or thread pool sizes that are too big, and the client is also often forgotten. So things to watch out for if you're doing this. And in the end, it was probably mostly an organizational challenge than a technical one. So we have a lot of teams, so we had to train them. We had to make the business understand that these fallbacks are important and better than big failure messages. But in the end, I think it really was worth it, and it probably saves a lot of money, or saved already a lot of money with these big outages. So to wrap up, failures are really not the exception. We need to deal with them. They are normal. So we need to be resilient against those failures. And a couple of techniques that we've seen to be more resilient is to implement these fallbacks, manage timeouts carefully, also for the clients, use bulkheading and load shedding to prevent that resource hijacking, and add circuit breaker to skip those futile calls to services that aren't healthy in any case. And adding resilience in the end doesn't really need to be really hard, certainly not with libraries that do it all for you. So that's it. I'm not sure how much time I have for questions, but